This is EGB320 Group 11 Lunar Rover Challenge, and our design challenge was to be able to get a rover to adhere to a number of design constraints such as fitting in a 15 by 15 centimeter box, the ability to move around a field, the ability to detect a green cube obstacle and move around it, the ability to detect a blue rock, move towards it and flip it over, the ability to collect an orange soil sample and return it back to the lander.
Hi, I'm Thomas. I'm in charge with mobility system. At first, we're starting the system with using two differential drive, but when testing it, the differential drive is not stable and it's falling off the lander with the caster touching in the dragging on the landers. So we changed it into a tank track because the tank tracks provide more tractions and balancing going up and down the landers. As you can see in the videos, the robot is stabilized up and on top of the landers when going down in the field as well. The tank tracks can give the robot going fast or slow, depends on the coding, but we decided to go slow for safety. And the tank tracks can do a 360 spins and a 180 spin to avoid obstacles. The movement, the maneuver is smoother with the tank track rather than the differential drive. Thank you.
Hey, I wanted to do a quick overview of my subsystem. So you can see here, that's where my subsystem is. So it has been changed from being a underscoop to just a pulley system with a servo here. And all it's doing is trapping the ball and then forking to tip the rock overhead. Here, sorry, I'll clear all the drawings. You can see how it actually works. So it gives all the information to the navigation system, but navigation system is the one using it. And it's actually tipping the rock and then looking for the ball again, still remaining in the up position, grabbing on the ball and closing up on it. There you go. So yeah, it's running on 50 Hertz, just like any servo should. And the important thing is that it's really just doing physical labor. It's not actually a lot of code. It's not transmitting information like its position anymore, like I thought it was going to do it at the very beginning. Thank you.
Hello, I'm Alex, and I'm in charge of the vision systems. My role is to be able to detect the objects collected from the Pi camera and feed the information to the navigation subsystem. Upon startup, the camera loop is initiated. By using the ball as an example, this loop goes to the following steps. First, a color mask is applied to the video, where the rest of the ball is separated from the rest of the image. Then, the largest area of the orange pixels, a box contour, is drawn around it. From there, a quick calculation can be made from the ball's center point, distance, and bearing. This process is also repeated for the rocks, obstacles, and lander. A similar method is applied for the lander hole and the walls, but instead of using a HSV color space, we used a grayscale, because it was easier to detect the black on each of the objects. Once this all happens, the distance, including bearing, object type, and object type, is returned to the navigation subsystem, which can then be fed into the other subsystems.
Hi, I'm Aaron. I'm in charge of the navigation component of the project. My role is to take the information from the robot's perception of the environment, in this case information taken from the robot vision subsystem, and decide on what the robot is to do depending on its state, and then give commands to the mobility system. To achieve this, a basic potential field method was used. This is where the robot is either attracted or repelled to objects in its view, depending on its state. An array is created with a peak at its heading of 0 degrees. Then whatever is in the field of view is added or subtracted from that array with the size or strength of that dependent on what it is and its distance from the robot. From this we can find the maximum value and what heading this correlates to. This information is then fed to the drive system to set the course of the robot. This system was implemented successfully. Here you can see the robot avoiding an obstacle and the wall and successfully capturing a sample that was initially obscured from view.